Welcome to the Deep Dive, the show where we cut through the noise and get you straight to the heart of what matters and, well, some pretty fascinating and incredibly relevant topics. Today, we're plunging into a world that honestly feels straight out of science fiction, but is rapidly becoming reality. How robots learn, how they perceive, reason, and act in our physical world. It's really a foundational shift in how we think about intelligent machines. We've poured over a comprehensive look at the modern paradigm of robotic learning, everything from the raw data that feeds them to the cutting-edge models that give them intelligence. Our mission today is simple: give you a shortcut, help you get truly up to speed on this complex area, understand its foundational element, the big challenges, and, the exciting future of truly intelligent robots.
And what's really revolutionary here, I think, is that this isn't just about making robots move from point A to point B anymore. The profound impact of data and these new learning paradigms. It's about creating adaptable generalist intelligence. It's about building a digital brain that can truly understand and interact with the physical world, not just, follow programmed commands. So as we unpack this, I'd really encourage you, the listener, to think about what surprises you most, or maybe what feels like a real game changer for how you see robots evolving.
Okay, let's unpack this then. To start, let's get down to basics. How does a robot actually sense its world? Like, what are the raw ingredients for robot intelligence? How are its experiences even recorded?
Yeah, that's absolutely the perfect place to begin. I mean, the development of intelligent robots fundamentally relies on the quality and, crucially, the diversity of their data. This whole data ecosystem, you could call it, is the sensory and experiential bedrock. And the choices you make in data modalities, what kind of senses you give it, and how that data is stored, well, that profoundly influences a model's capabilities and its ability to generalize later on.
Right. So when we talk about a robot's senses, are we talking purely digital stuff, or does it mirror human senses in some maybe surprising ways?
It definitely mirrors our senses, but often with even more precision, or maybe different kinds of precision. We can break them down into a few key categories. First, there's proprioceptive data.
Proprioceptive.
Yeah, it's essentially the robot's sense of self, its internal awareness, its body's exact position, its motion, the forces acting upon it. It's absolutely critical for stable control because it gives the robot this high-fidelity insight into its physical interactions, far beyond what it can just see externally.
Okay, so what exactly falls under this sense of self? Give us some specifics.
Sure. It includes things like the kinematic state, so the joint angles, velocities, torques of every part of its body. Think about how your brain knows where your arm is without you looking at it. That's proprioception, basically. Then there's force and tactile data, maybe from sensors on its gripper or other parts. Super important for delicate tasks like handling an egg without crushing it.
Right. Tactile feedback.
Exactly. And finally, inertial and electrical data. So things like accelerometers and gyroscopes for orientation, or even motor current readings, which can act as a proxy for how much effort a motor is exerting. Now, a significant challenge here is that this data comes from many sources, often at different speeds, asynchronously. It's like trying to listen to different instruments playing at slightly different tempos. So you need some pretty sophisticated pre-processing to synchronize these diverse streams for the learning models. And interestingly, in soft robotics, where you don't have rigid bodies, people are using novel things like magnetic sensors to help learn the robot's full 3D shape. It really shows that deep connection between the hardware and the learning.
Fascinating. So that's the internal awareness itself. What about how it perceives the outside world?
Right, that's exteroceptive data. And while it can include other sensor types, honestly, it's overwhelmingly dominated by visual information. We're talking imagery from cameras, and not just a single static camera usually. Often it's multi-view
I
setup.
don't know about you, like cameras everywhere.
Well, maybe a combination, like fixed cameras observing the whole workspace, and maybe wrist-mounted cameras for those close-up sort of egocentric views. This helps resolve occlusions, when something's hidden from one angle, and gives a much richer geometric understanding. Both standard RGB images and depth maps, which give you precise distance info, are super common. And in some advanced cases, again, like with soft robotics, magnetic field sensors can even infer interaction with external magnetic objects, which kind of blurs that line between internal and external sensing. It's pretty cool.
Okay, so it's got internal sensing, external sensing, visual mostly. How does it translate all that into actually doing something, into action?
That's where action data comes in. It's the language of control, basically, linking perception to physical effect. An action here is the specific control command issued to the robot to transition from one state to the next. This could be, say, target joint positions, or maybe end effector poses in 3D space, or even direct motor torques or velocities depending on the control scheme.
And how is that structured for learning? Is it just a list of actions?
Oh, well, the standard way to organize this for learning is an interleaved sequence of observations and actions. So, for instance, you'd have observation at time t1, then the action taken at t1, then the observation at time t, action at time t, and so on. This sequential format is absolutely fundamental to modern transformer models like RPT and Octo, which we'll probably talk more about.
Okay, we've talked about all this rich sensory data, proprioceptive, exteroceptive actions, but it sounds like a digital avalanche. For anyone who's ever wrestled with huge data sets, the next step is crucial.
Yeah.
How do you even begin to store this complex information efficiently so it's actually usable by these big models?
Yeah, you've hit on a really critical point about efficiency. The choice of data format is absolutely vital, especially with these large-scale models. Inefficient data loading can quickly become a crippling performance bottleneck. You spend more time waiting for data than actually training, and we've seen a pretty clear shift away from general-purpose, sort of human-readable formats like JSON and CSV.
Why is that? They seem convenient.
They are, for humans, but they store data row by row, which is quite slow for machine learning loads. The shift is towards specialized, high-performance binary formats.
Okay, so what's the big difference in these new formats? What makes them better?
It's primarily about columnar storage versus row-based. Imagine a giant spreadsheet of robot data, right? Time steps are rows, sensor readings are columns. In row-based formats, you read one entire row, one whole time step at a time, even if you only need the image and the action. But in columnar formats like Apache Parquet or ORC, all the values for a single data field say, all the images across all time steps or all the joint angles are stored together, contiguously.
Ah, I see. So you can just grab the columns you need.
Exactly. For machine learning, this is vastly more efficient because a data loader can read only the specific columns it needs, say just images and actions, without loading the entire record for each time step. This targeted access, plus much better compression algorithms, makes columnar formats the go-to for large-scale robotics. And Parquet, in particular, has really become the de facto standard. It's perfectly suited for that time series trajectory data that transformer models thrive on.
Can you give us a concrete example, a modern approach that maybe combines these ideas?
Certainly. The LeRobot dataset format, which Hugging Face has been promoting, is a great example of a modern kind of hybrid approach. It uses Parquet files for the structured time parts of a trajectory, like the robot's state, its actions. Then, for the high-dimensional camera observations, it uses standard MP4 video files, which are already highly compressed using standard video codecs.
Okay, so Parquet for numbers, MP4 for video.
Pretty much. And then JSON files hold the metadata, like information about the whole data set. It's a smart way to combine the high compression and efficient reads of columnar storage for trajectory data with established video standards. And a really crucial takeaway here is how open standards like Parquet enable collaborative learning. It makes it significantly easier for different research groups or companies to pool and share these massive data sets.
So it sounds like the very foundation, how a robot experiences and stores its world, isn't just some technical detail. It actively limits or enables what it can ultimately learn. That's a profound connection.
Precisely. It's the digital bedrock that underpins everything else. It influences everything from training efficiency right through to the potential for generalization down the line.
All right, so we've equipped our robot with senses, a way to record its experiences efficiently. But how does it learn from all that data? What are the fundamental ways robots turn that raw data into intelligent action?
Okay, now we get into the algorithms. We primarily look at two core paradigms, though they're often used in combination these days. The first is learning from interaction, and the main approach here is reinforcement learning, or RL. This is where a robot learns through, basically, autonomous trial and error. It takes actions, observes the results, gets some kind of reward signal, and tries to maximize its cumulative reward over time.
That sounds very intuitive, almost like how a child learns by playing, right? But what's the catch? Learning by pure trial and error in the real physical world must have some serious downsides.
Oh, absolutely. Its promise is undeniable. RL can discover truly novel strategies, especially for complex control problems like legged locomotion, where it's incredibly hard to explicitly program a good solution. However, its primary drawback is just immense sample inefficiency.
Sample inefficiency, meaning it takes tons of data.
Tons and tons. RL algorithms often require millions, sometimes even billions of interactions to converge on a good policy. Now, translate that to a physical robot. That's potentially infeasible amounts of time, a really high risk of damaging the robot or its environment, and just significant operational costs. Rating a robot for millions of trials isn't cheap. That's why pure RL, starting from scratch on real hardware, it's rarely done. Simulation becomes absolutely indispensable here.
Okay, so pure trial and error is too slow and risky in the real world.
Yeah.
What's the alternative that makes learning more practical?
That brings us to the second main paradigm, learning from demonstration or imitation learning, IL. This approach directly tackles RL's sample inefficiency by leveraging expert demonstrations often collected from human teleoperators guiding the robot. It drastically reduces the amount of data needed.
How does that work? Does it just copy the human?
Well, the simplest form is behavior cloning, BC, where the robot learns a direct mapping from observations to the expert's actions. Basically, yeah, it tries to mimic the expert. A more complex approach is inverse reinforcement learning, IRL, where the robot tries to infer the expert's underlying reward function, the why behind their actions, not just the what.
Okay, IL sounds way more efficient, especially compared to RL's millions of trials. But if a robot is just copying, does it ever get stuck? Like if the situation isn't exactly like what the human showed it, what are the limits there?
You've nailed it. Behavior cloning, the simpler form, can be brittle. It struggles with situations it hasn't seen in the demonstrations, and tiny errors can compound over time, leading to failure. And fundamentally, any IL policy is limited by the demonstrator's skill. It can't learn to perform a task better than the expert it's imitating.
So neither pure RL nor pure IL is perfect on its own.
Exactly. Recognizing these limitations, the field now largely uses hybrid approaches, combining the strengths of IL and RL. A really powerful strategy is to use human demonstrations to pre-train a policy, give it a good starting point via IL, and then fine-tune it with RL, often in simulation, to improve robustness and potentially surpass the demonstrator's skill level. The Rialto system is a great example of this. Uses a small amount of real-world IL data to bootstrap a policy, then makes it much more robust with extensive RL in a highly realistic digital twin simulation.
But wait a second, you keep mentioning simulation. If robots are learning so much in simulation, how do they handle the messy, unpredictable real world? This sounds like that classic reality gap problem. The simulation is never going to be perfect, right?
You've absolutely hit on arguably the most significant practical challenge in robot learning today, the sim-to-real or reality gap. It refers exactly to that performance degradation you see when policies trained purely in simulation are transferred to physical robots. It happens because of all those inevitable discrepancies, differences in physics, sensor noise, actuator delays, things you didn't perfectly model. Bridging this gap is critical for any practical robot deployment that relies on simulation for training.
So how do researchers bridge it? Do they just keep trying to make the simulation incredibly perfectly precise?
That was the old approach, but it turns out to be a losing battle. The primary and, frankly, most successful strategy now is called domain randomization, DR. And the philosophy here is almost counterintuitive. Abandon the quest for a single, perfectly accurate simulation because it's practically impossible to achieve. Instead, DR embraces uncertainty. It trains the policy across a wide distribution of simulated environments. During training, key parameters are intentionally randomized from one simulation episode to the next.
What kind of parameters are we talking about randomizing? Like they randomly change the lighting or the color of objects?
Exactly that, for visuals. Randomizing visual properties like lighting conditions, object colors, textures, even camera positions and angles, but it goes deeper into the physics too. We also randomize dynamics properties, things like the mass and friction of objects, the robot's motor torques, joint friction, even physical constants like gravity within a certain range.
Wow, so you're intentionally making the simulation less accurate in some ways, but more varied?
Precisely. By intentionally throwing all sorts of curveballs at the policy during training, changing the lighting, making objects unexpectedly slippery, even tweaking gravity slightly, the robot is forced to learn a policy that is robust to these variations. It learns to rely on the essential features of the task and ignore the superficial incidental details that might change.
So it learns a more general strategy.
Yes. The real world, with its own unique set of physical parameters, then appears to the trained policy as just another variation within the distribution it was trained on. It's learned to handle that uncertainty.
That's brilliant. It's almost like the robot's training becomes more general because it's forced to adapt to a chaotic, simulated world. It learns to see the forest for the trees, so to speak.
That's a great way to put it. This practical need for sim-to-real transfer actually becomes a powerful driver for generalization itself. it compels the models to learn more abstract, invariant representations. It's a really fascinating side effect.
Okay, all these breakthroughs we've just talked about, collecting vast amounts of data efficiently, the clever ways robots learn through interaction and demonstration, even beating the reality gap with domain randomization, they seem to have culminated in something truly game-changing. People are talking about the emergence of Robotics Foundation Models, or RFMs. What does this paradigm shift really mean for you, the listener, maybe someone thinking about using robots, and for the future of robotics itself?
Yeah, RFMs are a huge deal. If we connect this to the bigger picture, it's a fundamental move away from creating narrow specialist models towards building broad, generalist robot brains. The traditional approach was you train a distinct model for each specific task, each specific robot, each specific environment. It was incredibly costly and just didn't scale. You had to start over every time.
Right, a new brain for every job.
Exactly. RFMs are different. They are typically large models pre-trained on massive and crucially diverse datasets. This pre-training makes them adaptable to a broad range of downstream applications, often with minimal new data, sometimes even zero shot, meaning no new data, or few shot, meaning just a handful of examples. The goal is a single general-purpose system that can amortize those huge upfront training costs over many different applications.
So it's not just more data, it's smarter, more diverse data that's key here.
Absolutely. It's the diversity data from different robots, different tasks, different environments, maybe even different physical forms or embodiments that forces the model to learn the underlying abstract principles. Things like the general concept of grasping or pushing or navigating, which are common across many contexts. That's what leads to powerful generalization.
Okay, so what do these RFMs actually look like? Are there specific ones we should know about?
Well, the landscape is evolving rapidly, which is really exciting, but some prominent examples people talk about include RT2 from Google, which cleverly leverages vast amounts of web-scale vision and language data to derive knowledge it can use for robotic control. Then there's Octo, also involving Google DeepMind and others, which we should definitely dive deeper into. It focuses specifically on large-scale robot experience data using the Open X-Embodiment dataset.
Okay, RT2, Octo, and the others.
Yeah. RoboCat, another DeepMind project, is a general agent designed specifically to adapt quickly to new tasks across different real robot arms using few-shot learning. Crossformer is interesting because it aims to control a heterogeneous set of embodiments, different types of robots, without needing their action spaces to be perfectly aligned. And Hall-M is another Google effort, an embodied vision language model that essentially injects embodiment, the robot sensor data, into a large language model like Paul, allowing it to handle both language commands and robotics tasks together.
Wow, quite a few big players there. So are they all built the same way architecturally, or are there different approaches under the hood?
While there's variety, the dominant architectural choice currently seems to be the Vision Language Action VLA model. These typically use transformer backbones, very similar to the large language models like GPT or Paul-M that everyone hears about.
So transformers are powering robots too.
Largely, yes. Diffusion models are also emerging as a powerful alternative approach, particularly for generating smooth, continuous actions. And it's maybe worth distinguishing these end-to-end RFMs, which try to handle everything from perception to action, from systems that use large language models like GPT-4 as components, perhaps for high-level planning, like the SayCan system, for example, which uses an LLM to break down a complex instruction, bring me the apple, into feasible steps, but relies on separate, specialized modules for actual perception and low-level motor control.
That makes sense. And you mentioned open sourcing. How important is that?
Hugely important. Efforts like releasing the Octo model architecture and the massive Open X-Embodiment OXE datasets have been real catalysts. They significantly lower the barrier to entry for researchers and smaller companies, fostering this virtuous cycle of community contribution and competition, which ultimately accelerates progress for everyone.
Okay, let's do that deeper dive on Octo you mentioned. What makes it such an important case study for anyone looking at real-world robot applications today?
Octo is really an exemplary case study because it's an open-source generalist policy that truly embodies this foundation model paradigm. Architecturally, it's a transformer-based diffusion policy, but it's designed with immense flexibility and scale in mind. A key feature is its modular design. It has these input tokenizers. Think of them as specialized interpreters.
Interpreters for
different types of sensor data. One might handle multiple camera views, another the robot's internal state, that proprioceptive data we talked about, and another might take task specifications, perhaps given through language instructions, or even a goal image showing what the scene should look like. These tokenizers convert all these diverse inputs into a common digital language the main model can understand.
And then it funnels all that into one central brain to process everything.
Exactly. All those interpreted inputs feed into a shared transformer backbone. That's the core of the model. This backbone is what learns the shared abstract representation of the task and the state across all the different robots and environments it's been trained on. It finds the common ground. Then, after the transformer processes the inputs, a set of modular output heads, these are like specialized decoders, translate the robot's internal understanding back into concrete action commands. And importantly, these heads can be adapted to what that particular robot can actually do, its specific ways of moving, its action space.
That modularity sounds key. And the data it learned from, was it just one type of robot or many?
Oh, many. Octo's generalist capabilities come directly from its training data. It's pre-trained on a curated mix of 25 different datasets from that Open X-Embodiment or OXE collection. That amounts to over 800,000 real-world robot trajectories.
100,000.
Yeah, and crucially, this dataset is highly heterogeneous. It comes from a wide variety of robot arms, operating in different scenes, performing hundreds of different tasks. Imagine the sheer diversity of experience baked into that model.
Okay, so what can Octo actually do that's so game-changing for someone, say, trying to deploy a robot in their factory or lab?
Well, it primarily offers two major capabilities that stem from this pre-training. First, zero-shot control. For robot setups that were included in its pre-training data, Octo can often perform those tasks reasonably well out of the box with absolutely no additional training needed. Its performance is often competitive with much larger proprietary models in these cases.
Okay, so plug and play for known setups. What else?
Perhaps its most significant contribution is enabling efficient fine-tuning. Its modular architecture is specifically designed for rapid adaptation. A researcher or a company with a new robot or a specific new task can take the pre-trained Octo model, maybe swap in the appropriate output heads for their robot, and then fine-tune it on a surprisingly small dataset. We're talking maybe around 100 new demonstrations for a new task. And this fine-tuning process significantly outperforms training a similar policy entirely from scratch on just that small data set.
So if Octo is this pre-trained robot brain, does that mean a user with a new task or maybe slightly different robot arm could essentially just plug in Octo and then quickly teach it their specific trick with just a bit of data rather than starting the whole learning process from zero? How truly transformative is that for practical applications?
It's incredibly transformative, honestly. It signals a shift away from building a completely bespoke brain for every single robot and every single task variation. Instead, you're starting with a highly capable generalist foundation that already understands a lot about interacting with the physical world. Then you're just rapidly specializing it for your specific needs. This has the potential to dramatically reduce development time and cost, making sophisticated robot capabilities much more accessible to a wider range of users and industries.
Okay, but even with these powerful RFMs like Octo, you mentioned fine-tuning. A generalist model isn't instantly going to be an expert in my specific, perhaps unique task or environment. So this brings us to what you called the crucial last mile of training, fine-tuning. How essential is this step, really?
It's absolutely essential for bridging that gap between the broad pre-trained capabilities and the precise, reliable performance needed for a target deployment. Fine-tuning is what transforms that general knowledge into specialized expertise. It allows the model to really learn the specific nuances, the particular appearance of objects in your environment, the exact dynamics of your robot, the friction on your work surface. This leads to higher success rates and much more precise, predictable behavior.
So it improves accuracy. What other benefits does it provide? Why else is it so critical?
Well, beyond accuracy, it's crucial for domain adaptation. Adapting to the unique characteristics of the real-world deployment, like a specific robot's slightly different kinematics, or a particular camera's color balance, things that weren't perfectly captured in the pre-training data. And it enables embodiment specialization. While a generalist RFM might be trained on data from many different robot arms, fine-tuning specifically on data collected from your arm, say a Franca Emica Panda, allows the model to specialize its internal representations and control strategies for that arm's specific morphology and interface.
Right, making it work best for the body it actually has. So if I've got one of these amazing RFMs, how do we go about fine-tuning it? How do I get it from being a generalist robot brain to a specialist that's perfect for my unique setup? Are there different flavors or strategies for fine-tuning?
Yes, there's definitely a taxonomy of strategies, and each comes with trade-offs in terms of compute cost, data needs, and final performance. You have full fine-tuning, where you update all 100% of the model's parameters. This has the highest potential performance ceiling, but it's very computationally expensive, needs more data, and can be slow, often prohibitive for many users. Then there's sandwich fine-tuning, or partial fine-tuning, where you might train only a subset, say 10–20% of the parameters, often layers near the input and output. It's a more balanced approach.
Okay, full or partial? Any other options?
The really big shift, especially for practical robotics applications, has been the rapid adoption of parameter-efficient fine-tuning (PEFT) methods. The most well-known is probably LoRa, low-rank adaptation. And this isn't just some minor technical tweak. Its popularity directly responds to the economic and logistical realities of doing robotics in the real world.
How so? That sounds like a big claim. Why is PEFT such a big deal economically?
Because PEFT methods like LoRa involve training very few new parameters, often less than 2% of the original model's total size. They typically inject small, trainable adapter modules into the frozen pre-trained model. This drastically reduces the computational and memory requirements for fine-tuning. Why is this so crucial for robotics? Well, think about it. Collecting real-world physical robot data, getting those demonstrations, is incredibly slow, labor-intensive, and therefore expensive. You might need a human operator. The robot itself is occupied.
Robot time is expensive.
Exactly. PAFT means you don't necessarily need a giant GPU cluster and months of human demos to adapt a model. You can potentially adapt a powerful pre-trained global model with just a few hours of on-site data collection and training on much more accessible hardware. This slashes deployment costs and accelerates the process dramatically. It makes it feasible to customize models for many different specific scenarios. PEFT offers very good adaptation performance with very low computational overhead, making it the most practical choice for many, if not most, robotics applications today.
That makes a lot of sense. But it still sounds like fine-tuning a robot might be way more complicated, maybe even riskier, than just fine-tuning a chatbot to adopt a certain persona. What are the unique, perhaps even dangerous challenges involved?
You've hit on a critical distinction: the physical consequences. They make robotics fine-tuning uniquely fraught with risk compared to, say, language models. One major challenge is catastrophic forgetting.
Forgetting? Like the robot forgets how to do things.
Precisely. This is when a model, in the process of learning a new specific task, overwrites and effectively loses its previously learned general knowledge. For a language model, this might mean it forgets some facts. Annoying, but usually not dangerous. For a robot, it could be critical. Imagine fine-tuning a robot for a new assembly task, and in the process, it forgets fundamental safety constraints, like not colliding with obstacles, or basic physical common sense, like how to hold a tool properly. That could lead to damage or unsafe behavior.
Yikes, how do you prevent that?
Mitigation strategies exist, like elastic weight consolidation, EWC, which tries to protect important weights from the original training. Or simply using PAFT methods inherently helps because most of the original model remains frozen, preserving that general knowledge.
Okay, catastrophic forgetting is one risk. What else? Data is still an issue.
Absolutely. Data scarcity and quality remain a bottleneck even for fine-tuning. Acquiring that high-quality, task-specific demonstration data still requires physical interaction, which is inherently slow and expensive. And because you're often working with smaller data sets for fine-tuning, low-quality or noisy data can have an outsized negative impact. Garbage in, garbage out, especially here.
Makes sense. Any other big hurdles?
A really critical one is physical grounding and hallucination. Unlike an LLM hallucinating incorrect text, which might be nonsensical but harmless, an RFM can hallucinate physically impossible, unsafe, or simply nonsensical actions. The central challenge is grounding the model's abstract knowledge, perhaps learned from language or diverse pre-training, in the concrete physical reality of this robot in this environment right now.
Can you give an example of how they try to solve that grounding problem? How do they make sure the robot's abstract ideas are actually feasible in the real world?
The Seiken framework we mentioned earlier is a landmark example of trying to address this. It uses an LLM for high-level, common-sense reasoning, like figuring out that to clean the spill, I should probably get a sponge. That's the abstract part. But then, and this is the crucial grounding step, it combines this with a separate, learned affordance model. This affordance model evaluates the feasibility of each potential low-level action proposed by the LLM in the current physical state. So it checks, is there actually a sponge nearby? Can I physically reach it and pick it up right now? This grounds the LLM's abstract plans in the robot's learned understanding of its own physical capabilities and the current environment.
Ah, so a reality check module.
Essentially, yes. And finally, overarching all of this are the non-negotiables. safety, reliability, and real-time performance. Robotic failures can cause physical damage or injury. Models need rigorous testing, verification, and validation for safety and reliability. And they absolutely must run their inference cycle fast enough for real-time control, often needing decisions within milliseconds.
So it's really not just about making the robot smart in an abstract sense, but making it smart and safe and reliable in the real physical world.
Yeah.
That requires a whole different level of engineering rigor than, say, just generating a compelling essay or image.
Exactly. The stakes are just fundamentally higher when actions have physical consequences.
We've hammered home how critical data is for building these advanced robot brains. But collecting the massive, diverse data sets needed for RFMs, the Open X-Embodiment dataset you mentioned had 800,000 trajectories. That seems like a monumental hurdle. We're talking potentially petabytes of video force position data from potentially thousands of robots. My home server groans just thinking about my photo library. How do companies or research labs even begin to collect and manage the sheer scale of data needed for these cutting-edge foundation models?
It is a grand challenge, you're absolutely right. And attempting purely centralized data collection, where all the data from every robot gets sent back to one central server, it's fundamentally unscalable. It also raises huge privacy concerns, especially as we imagine robots moving into more personal spaces like homes or sensitive environments like hospitals. And just think about the logistics and the bandwidth costs. Uploading terabytes of high-frequency sensor data constantly from thousands, maybe millions of robots deployed globally. It's a practical and financial impossibility for learning at that kind of scale.
Okay, so centralized collection is out for massive scale. What's the solution then? Are they just going to rely even more heavily on simulation despite the reality gap?
Simulation will always be important, but the field is increasingly turning to decentralized approaches for learning from real-world data. And the leading paradigm here is federated learning, FL. Its core principle is brilliant in its simplicity. Train a shared global model across a network of decentralized devices, like a fleet of robots, without ever sharing the raw local data. This fundamentally inverts the traditional data pipeline. Instead of bringing all the data to a central model, FL brings the model to the data wherever it resides.
Okay, that sounds potentially huge for privacy. How does that actually work in practice? Walk us through it.
Sure. The typical process, often called centralized federated learning or CFL, proceeds in rounds. First, a central server initializes a global model, maybe the latest version of an RFM. That model is then sent out to a selected subset of participating robots in the fleet. Each selected robot then trains or fine-tunes that model using its own private local data, the experiences it's had recently. Now, crucially, instead of sending their raw sensor data back, the robots send only their updated model parameters, basically, the changes or gradients they calculated back to the central server, and this communication is often encrypted for extra security.
So they send back the learning, not the data.
Exactly. The server then aggregates these updates from all the participating robots. A common method is just averaging them, called federated averaging or FedAvG. This aggregation step creates an improved global model incorporating the collective experience. The process then repeats. The improved global model is sent out for the next round of local training. This allows the global model to continuously learn from the collective experience of the entire fleet while ensuring sensitive local data never leaves the individual robot. It preserves privacy, distributes the computational load, and even allows for some degree of personalization on the local device.
Wow. So potentially, my robot vacuum at home could contribute its learning about navigating tricky furniture layouts to improve the global navigation model for all similar robots, without ever sending a map or video of my living room to a central server. That genuinely feels huge for user privacy and trust.
That's precisely the promise. And what's also really interesting from a systems perspective is how the architecture of FL itself can be decentralized for even greater robustness. While CFL uses that client-server model, relying on a central orchestrator, there's also decentralized FL, DFL. This is a serverless, peer-to-peer architecture.
Peer-to-peer. The robots talk directly to each other.
Yes, in DFL, robots communicate and share their model updates directly with their neighbors in the network without needing a central server to coordinate everything. This eliminates the single point of failure associated with the central server and distributes the communication load across the network. It can be much more resilient, especially for a large fleet of robots operating in dynamic or potentially disconnected environments.
Fascinating. Are there real-world applications of this FL approach in robotics already, or is it mostly theoretical for now?
Oh, it's definitely moving beyond theory. FL is a very natural fit for things like robotic swarms, where groups of robots need to collaboratively learn shared behaviors or map an environment together. For fleet learning in autonomous vehicles, where uploading all sensor data is completely infeasible, FL allows vehicles to learn from diverse real-world driving scenarios encountered by the whole fleet. They might use cooperative data sampling strategies to decide which data is most valuable to learn from locally to optimize bandwidth.
Are there security concerns, like could a malicious robot send bad updates?
That's a major research area. Protecting the aggregation process from faulty or deliberately malicious robots, often called Byzantine agents in distributed systems literature, is critical. One promising direction is exploring secure DFL using blockchain technology. In such systems, each robot could act as a node, and shared model parameters or updates could be stored on a tamper-proof distributed ledger, with aggregation perhaps governed by secure smart contracts. And for practical implementation, people are actively developing frameworks to integrate FL directly with common robotics middleware like ROS2, the robot operating system, making it easier to build and deploy multi-agent collaborative learning systems.
This is really painting a picture where our future robots could be constantly getting smarter collectively, learning from each other's experiences almost organically, even without constant direct supervision from humans, and critically, without compromising our personal data. That's a truly networked intelligence that could evolve far faster than individual isolated units.
It really feels like the most viable path towards achieving truly scalable, private, and robust learning across large fleets of robots operating in the real world.
Okay, let's talk about the ultimate ambition now, the holy grail of robotic learning, true generalization. We're not just talking about adapting to a slightly different task or environment anymore. We're talking about policies that can adapt to completely new tasks, new environments, and this seems like the most challenging part, entirely new physical bodies. This is the ultimate dream, right? A single robot intelligence that isn't fundamentally tied to one specific physical form. But how on earth do you train something to control a quadruped if all its experience comes from a robot arm? Or vice versa? It seems almost impossible.
You've perfectly captured the frontier here. This is where the research is really pushing the boundaries. We're talking about policies that are truly general in a much deeper sense, moving beyond simple pattern matching or interpolation between similar tasks. The concept is often called cross-embodiment learning. The goal is to train a single policy, a single AI model, that can effectively control a heterogeneous collection of robots with significantly different morphologies. Maybe manipulator arms, quadrupeds, mobile bases, even drones.
A single brain for multiple bodies.
Essentially, yes, an omni-bodied or general-purpose robotic brain. Closely related is the practical goal of hardware-agnostic learning. This aims to decouple the robot's intelligence from the specific physical components it's made of, the brand of arm, the type of camera, the specific gripper. The practical benefits here are huge. Flexibility in choosing hardware, reduced costs, escaping vendor lock-in, fostering a more open market for robot components. Ideally, data collected on one type of robot could be used to train a policy deployed on a completely different robot.
So the dream is no more having to completely reteach the robot intelligence every time you upgrade the hardware or switch out a part. That would be massive. But how? How do they possibly achieve this without just building a unique brain module for every single robot type?
The key technical enabler, the magic ingredient, if you will, seems to be learning abstract and disentangled representations. Instead of learning brittle end-to-end mappings like these specific pixels mean apply these specific torques, which are obviously tied to this specific camera and specific motors, these generalist models learn an intermediate, more abstract representation of the task and the environment state.
Abstract and disentangled. What does disentangled mean here?
It means the model learns to internally separate out the independent factors of variation in the world. So it might learn separate representations for, say, 1, the robot's own embodiment, its shape, its kinematics, what it can do. 2, the task-relevant objects in the scene, like the block that needs to be picked up. And 3, the broader environmental context, like static obstacles, the layout of the room.
And separating these helps generalization.
Massively. By disentangling the abstract task goal, e.g., get the red block to location X, from the specifics of the current embodiment and the current environment, the model can potentially generalize that task knowledge across different bodies and different contexts. Language is proving to be a really powerful tool here for learning these kinds of abstract, embodiment-agnostic representations. The command pick up the apple doesn't specify how or with what kind of gripper. It's an abstract goal.
That makes intuitive sense. It's almost like teaching a robot to think conceptually about the goal, rather than just reacting reflexively to its immediate sensor inputs. Can you give us an example of how this extreme generalization actually plays out in recent research? Has anyone really done this?
Yes. This leads us to consider just how broad this cross-embodiment transfer can go. Some really exciting recent research, for instance, the work around cross-former, has pushed this concept almost to its limits. They've demonstrated a single policy, trained jointly, that can control multiple, very different robot types: traditional manipulator arms, quadcopters, legged quadrupeds, and wheeled mobile bases.
A single policy for all of those. How? They seem so different.
The unifying insight, or hypothesis, driving this work is that seemingly disparate domains like robotic manipulation, moving arms, and navigation, moving vehicles or drones, actually share fundamental sensor and motor principles. Both require understanding 3D geometry, reasoning about collision avoidance, visual servoing towards a goal. There are underlying commonalities in how an agent needs to perceive and act to achieve goals in physical space.
Okay, that's the theory. And what were the results when they actually trained a single policy on both manipulation and navigation data? Did it just average out the performance, or was there a true synergy?
This is where it gets really profound. The empirical results showed significant positive transfer between these domains, meaning the policy actually performed better on manipulation tasks, for example, showing around a 20% average improvement in success rate when diverse navigation data was included in its training mix, compared to training only on manipulation data, and vice versa. Navigation improved when manipulation data was added.
Wow, that's not just generalization, that's synergy. It's like teaching a child to walk helps them learn to play soccer better later, even though you didn't specifically teach soccer skills during walking practice. The underlying skill of balance and coordination transfers.
Exactly. It strongly suggests the model isn't just memorizing separate skills, but learning a more robust, more general internal representation of goal-reaching behavior in 3D space that benefits both domains. And the ultimate demonstration of this was achieving zero-shot transfer to a completely novel embodiment. A policy trained only on separate manipulator arms and separate mobile bases was successfully deployed on a mobile manipulator, a robot with both an arm and a moving base, a combination it had never seen during training, and it worked effectively without any specific fine-tuning for that combined system.
That is genuinely astonishing. Controlling a novel body type with zero specific training for it? Yeah. What's the architectural blueprint behind this kind of extreme cross-embodiment generalization? How did CrossFormer enable this?
The cross-former architecture provides a pretty clear blueprint for how this can be achieved. It typically uses modality-specific input tokenizers, just like Octo, to handle the different sensor inputs from potentially different robots. These all feed into a large shared transformer backbone. This central core is where the shared abstract representation across all embodiments and tasks is learned. But then critically, it uses embodiment-specific action heads. These are separate, usually lightweight output modules that translate the abstract embeddings generated by the shared backbone into the specific action formats required by each different robot class. For example, joint torques for an arm, velocity commands for a mobile base.
So the brain is shared, but the mouth speaking the commands is specific to the body.
That's a great analogy. This architecture explicitly decouples the general intelligence residing in the backbone from the specific hardware interface handled by the heads. And the implication here is potentially revolutionary for the industry. It suggests a future where robot brains, the foundation models, and robot bodies, the physical hardware, could potentially be developed and even sold as separate interoperable components, much like we see with hardware and software in the computing industry today.
Okay, we have covered a lot today. From the basic senses of a robot and how they store data efficiently, through the different ways they learn, bridging the reality gap, the rise of generalist foundation models, the need for fine-tuning, scaling data collection with federation, all the way to these incredible cross-embodiment capabilities. I'll try to bring it all together now. If you zoom out, what does this integrated pipeline of modern robotic learning look like from start to finish?
Yeah, it's helpful to see it as an end-to-end journey where each stage builds on the last. It really starts with the data foundation. That means collecting massive, diverse, multimodal data and crucially, storing it in efficient, standardized formats like Parquet to enable large-scale processing. Then, to actually acquire that data at scale while maintaining privacy, we have decentralized acquisition, primarily using federated learning to overcome logistical bottlenecks and learn safely from real-world fleets.
Okay, so the data gets collected, stored efficiently, and privately managed. Then what happens with it?
This data feeds into the learning paradigms. Today, that typically means a powerful hybrid approach, using imitation learning from demonstrations for an efficient starting point, combined with reinforcement learning, often mainly in simulation, for robustness, optimization, and discovering potentially superhuman strategies. And absolutely critical in this phase is domain randomization to bridge that persistent sim-to-real gap and, as a beneficial side effect, force the models to learn more generalizable behaviors.
And all this training culminates in?
It culminates in foundation model pre-training. This is where these large general-purpose RFMs like Octo or others are created. They learn those abstract representations of physical interaction across a vast range of tasks, environments, and maybe even robot types included in the pre-training data.
So you have the big generalist brain.
Yeah.
But we know it needs specialization.
Exactly. The next step is specialization via fine-tuning. This is where those powerful pre-trained RFMs are efficiently adapted for specific real-world applications, often using parameter-efficient techniques like LoRa. And this stage requires carefully navigating the complex challenges of physical grounding, safety, and avoiding catastrophic forgetting.
And the ultimate goal driving this whole pipeline.
The ultimate goal, the frontier we're pushing towards, is the generalization frontier, producing truly general policies capable of cross-task, cross-environment, and ultimately cross-embodiment transfer by learning those deeply abstract and disentangled representations. This enables the vision of hardware-agnostic robotic intelligence.
That's an incredible, integrated vision of how modern robots learn. But let's be realistic. What are the big challenges still ahead? For you, the listener, maybe thinking about deploying robots, or for the researchers and engineers actually building these systems, what's keeping people up at night?
Oh, despite the remarkable progress, significant challenges absolutely remain. One challenge that immediately comes to mind, and it's been a theme throughout our discussion, is the data bottleneck. Getting enough high-quality, diverse, real-world data is still often the primary constraint. Physical data collection is just inherently slow, expensive, and sometimes dangerous.
Right. Data is still king and hard to get. What else?
Safety and reliability are paramount, especially as robots move into human-centric environments like homes, hospitals, or collaborative workplaces. We need much more rigorous methods for testing, verification, validation, and perhaps even formal guarantees or ways to quantify the uncertainty in a robot's decisions. How can we truly trust them? Then there's the constant tension regarding real-time performance. These foundation models are getting huge, often with billions of parameters, but robot control often requires extremely low latency decisions in milliseconds. Squaring that circle, getting large model intelligence to run fast enough on potentially resource-constrained robot hardware requires ongoing advances in model compression, quantization, specialized hardware acceleration, and efficient algorithms.
Makes sense. Big models versus fast reflexes. Anything else?
A huge one is explainability and interpretability. The black box nature of these large, complex models makes it incredibly difficult to understand why a robot made a specific decision, especially a wrong or unexpected one. Better explainability is crucial not just for debugging and improving the models, but also for building user trust, ensuring accountability, and potentially for certification and safety-critical applications.
Okay, data, safety, speed, and understanding why. Those are definitely big hurdles. So given all this progress, but also these remaining challenges, where is all this leading? What are your predictions for the future trajectory of robotic learning?
Looking forward, I think several trends are likely to define the next phase. One is the probable emergence of a more clearly defined robotics AI stack. We might see the industry stratify into different layers. Companies specializing in building the physical robot bodies, hardware, maybe data-as-a-service providers managing large-scale data collection and curation, core foundation model players developing the base RFMs, and then application specialists who focus on fine-tuning these models for specific vertical markets or customer needs.
Interesting, a whole ecosystem. What else?
Simulation will become an even more foundational tool, I believe, not just for initial training, but throughout a robot's life cycle. We'll see wider use of high-fidelity digital twins, virtual replicas of real-world deployments used continuously for testing updates, robustifying policies against new scenarios, and performing extensive safety validation before deploying changes to physical robots.
Okay, more specialized industry roles, better simulation. How about the robots themselves? What new capabilities might we see?
I expect we'll see progress towards truly embodied multimodality. This means integrating richer sensory data beyond just vision and basic proprioception. Think about incorporating advanced tactile sensing across the robot's body, force feedback, maybe even audio understanding, to enable a more holistic, human-like grasp of the environment and allow for much more delicate and nuanced physical interaction. And finally, the edge AI imperative will only intensify. The need to deploy powerful AI intelligence directly on the resource-constrained robot hardware itself rather than relying constantly on the cloud is critical for autonomy, responsiveness, and privacy. This will drive further advances in parameter-efficient fine-tuning, PEFT, knowledge distillation, compressing large models into smaller ones, and the development of specialized AI accelerator hardware designed for robotics workloads.
So wrapping this all up, what does this deep dive mean for you, the listener? It seems clear that from sensing its own body position to collaborating on learning across a vast fleet, robots are fundamentally shifting. They're moving from being pre-programmed specialist tools towards becoming truly versatile, adaptable partners. There's really a shift from robots that do what they're told to robots that learn how to do things.
Indeed. And the ultimate goal of this transformation really is to create robots that can learn to help almost anyone, with almost anything, almost anywhere. It promises a future where sophisticated robotic assistance isn't confined to structured factory floors, but can be integrated much more flexibly and seamlessly into the complexities of everyday life and work.
This whole deep dive really suggests that the robots of the future might not just be programmed by engineers to do a specific job. They might be more like universal apprentices, taught by experience, both their own and collective, to learn and adapt to new challenges. Just think about that for a moment. What kind of entirely new problems could we solve? What new possibilities open up if robots could truly understand the physical world and how to interact with it effectively across almost any physical form they might take? We really hope this deep dive into the fascinating world of robotic learning has given you some surprising insights, maybe clarified some confusing concepts, and ultimately provided a clearer picture of this incredibly rapidly evolving field. As always, we encourage you to keep exploring, keep asking questions.